How do modern apps like Discord, Figma, or Binance push thousands of live messages and price updates straight to your screen at the exact millisecond without you ever having to hit refresh? The traditional web is built on HTTP, a stateless request-response protocol. The client must first send an explicit request, and the server processes that request and sends back a response. And then the underlying TCP connection immediately closes. But what happens if the server gets new data, like a sudden Bitcoin price spike or a new message, and wants to send it to the client immediately? In standard HTTP, the server cannot initiate contact. It can only speak when spoken to. And that is where our real-time architecture problem begins.
To bypass the limitations of traditional HTTP, engineers first invented HTTP short polling. In short polling, the client sets an automated timer and spams the server with HTTP GET requests every single second, constantly asking, is there new data yet? Is there new data now? 99% of the time, nothing has changed. So the server responds with empty 200 OK payloads over and over again, wasting massive amounts of server CPU and network bandwidth. Why is short polling so inefficient? Because every single HTTP request carries heavy HTTP headers, ranging from 500 bytes to 2 kilobytes, containing cookies, user agent strings, and security tokens for just a tiny 2-byte payload. To improve this, engineers introduced HTTP long polling. In long polling, the client sends a request, but instead of responding immediately, the server holds the connection open and waits until a new event actually occurs on the backend. While long polling reduces empty requests, it still suffers from connection teardown overhead, latency spikes during reconnections, and severe server socket exhaustion.
In 2011, the Internet Engineering Task Force released RFC 6455, officially introducing the WebSocket protocol to fix real-time web communication forever. The brilliant design choice of WebSocket was to reuse standard web ports, port 80 for HTTP and port 443 for HTTPS, allowing it to pass seamlessly through existing corporate firewalls and proxies. Everything begins with an initial handshake. The client sends a standard HTTP GET request, but inserts 2 mandatory upgrade headers. Upgrade equals WebSocket, and connection equals upgrade. Along with these headers, the client includes a randomly generated 16-byte value encoded in base 64, known as the sec WebSocket key. When the server receives this handshake, it doesn't just blindly accept it. It validates the challenge using a strict mathematical formula. The server takes the client's key, appends a globally unique magic GUID string, computes a SHA-1 hash, and encodes the result in base 64, producing the exact matching token required for the sec WebSocket accept response header. The server then responds with HTTP status code 101 switching protocols, along with the calculated accept key. At this exact millisecond, the HTTP protocol steps aside completely. The temporary HTTP connection upgrades into a persistent bidirectional TCP tunnel that remains open indefinitely until explicitly closed. A classic mistake in system design interviews is assuming that every real-time feature requires WebSockets. In reality, choosing the right protocol depends on data direction, transport layer constraints, and architectural complexity. First, server-sent events, or SSE. If your application only needs data flowing in one direction, from the server down to the client, SSE is usually the superior choice. It runs over standard HTTP2, supports native automatic reconnection, and effortlessly traverses firewalls without custom protocol upgrades. Second, WebSockets. When you need interactive, low-latency, two-way communication between a client and a central server, WebSockets are the industry standard. Because it operates as a full-duplex TCP tunnel with minimal frame overhead, both sides can push messages at any sub-second interval. Third, WebRTC. What if your application requires ultra-low latency audio, video, or high-throughput data streams directly between users without routing all media through your backend servers? WebRTC creates direct peer-to-peer UDP connections using a signaling server only for the initial handshake. Here is your definitive system design decision guide. Use SSE for one-way server-to-client streaming, like AI responses. Use WebSockets for interactive client-server chats and games. And use WebRTC for peer-to-peer audio, video, and high-frequency binary data. To summarize, WebSocket transforms a simple HTTP handshake into a powerful, persistent TCP tunnel. By eliminating the heavy overhead of HTTP headers on every single request, it provides a full duplex connection where both the client and server can push updates instantly, enabling true real-time experiences. Here is your final system design production architecture snapshot. It highlights how multiple clients connect through a Layer 4 load balancer to a scaled cluster of stateful WebSocket servers, which are interconnected by a high-speed Redis pub/sub message bus to synchronize state and broadcast data effortlessly. Save this video for your next system design interview or technical architecture review, and subscribe for more deep dives into the core infrastructure powering the modern web.